In this video, we solved problem number 2 from quiz number 6, which is all about classifying differential equations um, and just sort of talking through how you would go about solving a particular differential equation. So here's the problem statement. It says for each of the following differential equations, classify the differential equation as homogeneous or non-homogeneous, then identify the method or methods that may be used to solve the differential equation and the corresponding homogeneous DE if appropriate. Then describe the form of the solution, the form of y sub c, the form of y sub p if appropriate, and the form of the general solution. And then it says choose from among the following methods. We know how to solve homogeneous differential equations that are linear and have constant coefficients, Cauchy-Euler differential equations. We know how to use the method of undetermined coefficients and the method of variation of parameters to find y sub p. Now, if none of those solution methods are appropriate, then we would use the series solution method. And hopefully we can use a series solution method about an ordinary point, that is provided that x not equals 0 is an ordinary point. If it's not, if it's a singular point, well, we cannot solve it using the methods that we have talked about so far in our class. Okay, so this is just what you can expect. For each differential equation, I'm going to ask you to classify it as homogeneous or non-homogeneous, and then we want to choose the appropriate method or methods. If it's non-homogeneous, you're going to have a method for solving the homogeneous equation and a method for solving the non-homogeneous equation. If it's a homogeneous equation, there's only one method. And then here you'll state the form of the solution of the corresponding homogeneous differential equation. All I'm looking for there is that form of the initial guess. You say, okay, I'm looking for a solution of this form, y equals e to the mx, y equals x to the m, y equals this infinite series. That's what will go there. And then if appropriate, if you've got a non-homogeneous equation, I'll want you to state the form of y sub c. If you have a non-homogeneous equation, I'll want you to state the form of y sub p, and then I'll want you to state the form of the general solution. We're going to do this for about 5 differential equations, and I will walk you through my solutions now. So here's our first differential equation. Actually, I'll share my paper with you. So here's my first differential equation. I notice that when my y's are all on this side, I've got my y here, my y double prime, and my y triple prime here. The right-hand side is non-zero, so that makes this a non-homogeneous differential equation. Then in order to choose the appropriate methods, I'm going to have to choose 2 methods, one for the corresponding homogeneous equation, which we're denoting d sub h or dE sub h, and then we'll choose an appropriate method for the non-homogeneous equation. Now, if I make that right-hand side 0, and I look at this left-hand side, I notice I've got a constant times x to the third times the third derivative of y with respect to x. Since the power of x and the order of the derivative multiplying it are the same, that is potentially a Cauchy-Euler differential equation. Now I have to check that condition for every term on the left-hand side. So over here, I've got a constant times x squared times the second derivative. That's a second power and a second derivative. So that is appropriate for Cauchy-Euler. And on this one, we've got the 0th derivative and an x to the 0. So that's appropriate for Cauchy-Euler as well. So the corresponding homogeneous equation is a Cauchy-Euler differential equation. Now, since we've got a right-hand side that's non-zero, we have to solve that, this equation that we started with for y sub p. Now, we cannot use the method of undetermined coefficients here because the method of undetermined coefficients only applies when the corresponding homogeneous equation has constant coefficients, and our coefficients depend explicitly on x. So if this differential equation is Cauchy-Euler, you have to use variation of parameters to find y sub p. Okay, so now we want the form of the solution for the Cauchy-Euler equation. Well, we'll just let y equal x to the m. And then the form of y sub c depends on the order of the differential equation. Since that's third order, y sub c is going to have 3 terms. We're going to have 3 linearly independent solutions that are approximately of the form x to the m. It depends, the form may change depending on whether that characteristic equation of the differential equation has distinct real roots or complex conjugate roots or repeated roots, repeated real roots or repeated complex conjugate roots. After you find the values of m that satisfy that characteristic equation, you'll have three solutions, y sub 1, y sub 2, and y sub 3, linearly independent from each other, and y sub c will have this form. Okay, so it was a third order equation. The form of y sub p in that case is u1, y1 plus u2, y2 plus u3, y3, where u1, u2, and u3 satisfy these equations. Now w in the denominator is the Wronskian of y sub 1, y sub 2, and y sub 3. And w sub I looks just like that Wronskian, but instead of that ith column, it'll be replaced by 0, 0, and f of x. So w sub 1 has a 0, 0, and f of x in the first column. W sub 2 has 0, 0, and f of x in the second column. And w sub 3 is going to have 0, 0, and f of x in the third column. And if you're saying to yourself, what is f of x? To find f of x, you take this differential equation, you divide out that leading coefficient because we need the leading coefficient to be 1 in order to identify f of x. When we do that, we get this, which simplifies to 1/10. So our f of x is 1/10. So that's the first one. And then the form of the general solution is y sub c plus y sub p. Here's our next one. I've got this differential equation. Notice it's second order. And with the y's over here and the function of the independent variable only on the right-hand side, we see that that right-hand side is non-zero. So this is a non-homogeneous differential equation. That means we're going to have to solve two equations. We'll have to solve the corresponding homogeneous equation and the corresponding and the differential equation itself for y sub p in order to get the general solution. So now we think about the corresponding homogeneous equation. That's where we have this equal to 0. Well, if that's a 0, we look at the left-hand side. The coefficients on the left-hand side are just 1, -2, and 5. So that's a constant coefficient linear differential equation, and it would be homogeneous at that point. So the method that we'll use is the one for homogeneous linear ODEs with constant coefficients. Now, since the right-hand side depends on t, the form of the solution for that constant coefficient equation is not e to the mx, but e to the m times the independent variable, which in this case is t. Then for the right-hand side, or for the differential equation that we have here, when we're trying to solve for y sub p, we need to use one of two methods. Now, both the method of undetermined coefficients and variation of parameters are appropriate here. You don't have to have both of these on your quiz. You just pick one of them. I would choose the method of undetermined coefficients. Since this is an exponential times a cosine function, I would guess that y sub p is an exponential times this quantity, a constant times a cosine plus a constant times a sine for unknown constants a and b. That would be my method of choice. But variation of parameters always works for finding y sub p. So you could use you could use variation of parameters here. Since the differential equation is second order, y sub p would be u1 y1 plus u2 y2, where u1 and u2 satisfy these equations, and these are our w's. And then, so either one of those is fine. Since the differential equation was second order, the form of y sub c is c1 y1 plus c2 y2. That means and then the form of the general solution is y sub c plus y sub p. So we'll have this plus this for the right functions y1, y2, and u1, y1, or u2, or u1 and u2 there. Okay, let's do another one. This one we can do together. Actually, I had all that written down because I did a first take of this, and then I was stumbling over my words as I was explaining this the first time, so I'm going to try again. We've got this differential equation over here. Notice that when all the y's are on this side, the right-hand side is 0. So, and we don't have any terms involving just the independent variable x. So that makes this a homogeneous differential equation. Since it's homogeneous, we only need one method. Now, we want to choose the appropriate method here. We only have three methods for solving homogeneous equations. We have the method for homogeneous linear ordinary differential equations with constant coefficients. We have the method for Cauchy Euler differential equations. And then if neither of those work, we can always use a series solution about an ordinary point. Well, these coefficients are not constants, so the first method is out. For the second method, Cauchy Euler, I just look at that first coefficient and I can tell the differential equation is not Cauchy-Euler, because in order for this to be a Cauchy-Euler differential equation, this leading coefficient would have to be a constant times x squared. I've got an x squared plus of 2x. That 2x makes it not Cauchy-Euler. So this neither has constant coefficients nor is a Cauchy-Euler differential equation. So the only method that is appropriate based on what we've studied is a series solution method. Ooh, but we aren't able to solve this as a series solution about an ordinary point. So I think I'm going to give everyone full credit for this. This would require what's called a series solution about a singular point, x naught equals 0. And the form of the solution in that case is the sum as n goes from 0 to infinity of c sub n times x to the n plus r, where r is a value to be determined by us, provided that x naught equals 0 is a regular singular point of the differential equation. Now, we did not talk about that, so I'm going to omit this one from your quiz. I'm seeing it now and realizing that that is a singular point rather than an ordinary point. Sorry about that. I shouldn't have written this question on this quiz in that way. But hopefully that alludes to this possibility of finding a series solution about what's called a regular singular point. If you are interested in learning that method, let me know. I've got materials for that method, and you can earn some extra credit if you want to do some self-study of series solutions about regular singular points. It's called the method of Frobenius. Sometimes called Frobenius's method. Depends on the book. But you're going to seek solutions of this form. And then the general solution actually depends on the values of r that you get when you substitute this into the differential equation. But since it's a second order equation, you know that the general solution will have this form, c1y1 plus c2y2, where c1 and c2 are constants to be determined, and y1 and y2 will have a form something like this. One of those will be a series solution, and the other one may or may not be a series solution. Might be a series involving a natural log, or just like a natural log term, and then there's a series term. It's kind of cool. You have to check out that method of Frobenius if you are interested in that. Okay, I'm going to put the next problem up here now. Okay, so we're going to keep going. Now we've got this differential equation. Notice that the variables are different, but we don't want to let that bother us. We can handle any variable that they throw at us, right? Because we understand the forms of differential equations. This is a constant times t to the fourth times the fourth derivative of x with respect to t. And then I'm adding a constant times t squared times the second derivative of x with respect to t. And then I've got a constant times x here equals a natural log of t. Since this side involves x and x's derivatives, and this side involves the independent variable t only, and there are no other terms involving the independent variable t only, I can just look at this, look at the right-hand side, and since it's not 0, I can say that this differential equation is non-homogeneous. So that means we're going to need two methods. We need a method for solving the corresponding homogeneous equation and a method for solving the non-homogeneous equation. Well, the corresponding homogeneous equation, if that's a 0, is actually Cauchy-Euler, because notice that the power of t and the order of the derivative multiplying it are the same. That's true here, and that's true here. And if you're saying there are no powers of t here, you're right. But you can think of that as t to the 0 times the 0th derivative of x with respect to t. So this is a Cauchy-Euler differential equation. And since the coefficients depend explicitly on t, we can't use a method of undetermined coefficients to solve the corresponding non-homogeneous equation. So we have to use variation of parameters here. Okay, so now the form of the solution of the corresponding homogeneous equation is the form of the solution for a Cauchy-Euler DE. So here we're going to let x be a function of t, and rather than having y equals x to the m, we're going to have x of t equals t to the m. And I guess it shouldn't be y sub c, it should be x sub c. And in this case, we'll have x sub p here. Now, since it's a fourth order equation, x sub c will have this form: c1 x1 plus c2 x2 plus c3 x3 plus c4 x4. And x sub p will have the form u1 x1 plus u2 x2 plus u3 x3 plus u4 x4, where u1, u sub 2, u sub 3, u sub 4 are all non-constant functions, so that x sub p is linearly independent from x sub 1, x sub 2, x sub 3, and x sub 4. And those have to satisfy this. u1 prime is going to equal to w1 over w. Actually, let's just write u sub I prime is equal to w sub I over w. This is for I equals 1, 2, 3, and 4. And w is the Wronskian of those, four solutions: x sub 1, x sub 2, x sub 3, and x sub 4. So this is a 4 by 4 determinant. And you just take the derivatives as many times as necessary until you get 4 rows. Okay, and then w sub I is going to look just like, and I was writing equals, but I'm going to write over that. I'm going to say that w sub I is also a determinant. It's similar to w, where the ith column of w is replaced by 0, 0, 0. And then f of t, and f of t is what we get when we take this differential equation and we force the leading coefficient to be 1. So we want to divide everything by t to the 4th here. The right-hand side there is our f of t. So in this case, the ith column is going to be replaced by that. And that's natural log of t over t to the 4th. Okay. The form of the general solution is then x equals x sub c plus x sub p. We just take those that we just found and we add them together, and that's the general solution. Okay, let me write down the sort of setup for the next differential equation, and then we'll go over that one. Okay, guys, this is the last one. We've got this differential equation. Notice y and y's derivatives are on the left-hand side. There are no terms involving just the independent variable only. We don't even know what the independent variable is. So this is homogeneous, definitely. When I look at the coefficients of the left-hand side, I see that they're 1, 3, and -2. So the method here is the method for solving homogeneous, linear, ordinary differential equations with constant coefficients. The form of the solution of this is y equals e to the mx, if we're assuming that that independent variable is x. And it's really not appropriate to talk about the form of the solution y sub c or y sub p because it's a homogeneous equation. But I notice that it's a 5th order differential equation. So this will correspond to a 5th degree characteristic polynomial, or characteristic equation, which involves a polynomial in M, a 5th degree polynomial in M, set equal to 0. So we're going to have 5 values of M that will cause functions that look like this to be solutions to that equation. And so in that case, we'll have 5 linearly independent solutions in our fundamental set. So y will equal c1 y1 plus c2 y2 plus c3 y3 plus c4 y4 plus c sub 5 y sub 5. Those, we take our 5 linearly independent solutions, we multiply them by constants, and we add them together. And that is the form of the general solution. So that is the end of problem number 2 from quiz number 6. Let me know if you guys have any questions.